Welcome back to the explainer. Okay, let's jump right into this. Have you ever actually stopped to think about the invisible supermaterial powering our modern world? I am talking about a highly engineered substance that's so incredibly versatile. It's used in everything from the softest, safest baby pacifiers to the insanely high-stress environment of automotive turbochargers. Today, we're demystifying silicone rubber. We are going to figure out exactly how this material works, stripping it all the way down to its atoms, and then building it back up to see how it solves massive industrial challenges. Here is our roadmap for today's explainer. We'll kick things off with origins and chemistry, then look at solid versus liquid rubber. Next, we'll dive into formulating the perfect mix, followed by 2 ways to cure, and finally, we'll wrap it all up with everyday material superpowers. All right, part 1, origins and chemistry. We're going from sand to the silicone backbone. So where does this highly advanced polymer actually come from? Believe it or not, before it becomes a complex, high-tech elastomer, it begins its life cycle as something incredibly humble and abundant, simple quartz sand. To understand how an endless supply of sand turns into a supermaterial, we have to look at the chemistry. It all comes down to the silicon atom itself. A silicon atom has 4 valence electrons, which basically means it has 4 potential connection points to link up with other atoms. In materials science, this is usually abbreviated with the letter Q, standing for the quaternary group. And this 4-point connection, that is the absolute architectural foundation of all silicone rubber. It's the building block that makes the whole shebang possible. Now, check out the math here because it is a total game changer. If you look on the left, the backbone of silicone rubber is made of alternating silicon and oxygen atoms, the Si-O link. This specific chemical bond has an incredibly high bond energy of 451 kilojoules per mole. Compare that to the right side. Traditional organic rubber is built on carbon-to-carbon links, which only have a bond energy of 352 kilojoules per mole. That numerical difference is literally the secret to silicone superpowers. It takes significantly more energy, meaning way more heat or physical stress, to break a silicone bond than an organic rubber bond. That's exactly why silicone is inherently more durable and heat-resistant. Let's picture how this structure actually takes shape. Notice that main chain right down the middle, that alternating silicon-oxygen silicine backbone we were just talking about? But look at what is attached to the sides. Those are organic side groups, like methyl or vinyl groups, and they act like a physical force field. They literally shield the backbone from outside elements. This shielding effect gives the material a very low surface energy, which, if you're wondering, is exactly why silicone has that famously incredible water-repellent quality. Moving on to part 2, solid versus liquid rubber. It's all a matter of chain length. Here we have a great side-by-side of the 2 main classes of uncured silicone. Over on the left is solid silicone rubber, also known in the industry as high-consistency rubber or HCR. Chemically, this stuff is made of polymers with very high molecular weight and incredibly long polymer chains. Because those chains are so long, it physically behaves like a solid, and it's delivered to factories as thick, heavy bars wrapped up in film. But on the right, we have liquid silicone rubber, or LSR. This formulation uses shorter polymer chains with a lower molecular weight, and because the chains are shorter, it flows easily. It's delivered in these distinct 2-part drum systems, an A component and a B component, ready to be pumped directly into injection molds. It's just a perfect example of how the chemistry dictates the physical form, which in turn completely changes how industries process it. All right, part 3, formulating the perfect mix. Let's look at compounding the silicone recipe. Think of that raw silicone polymer we just discussed, kind of like raw dough in a bakery. On its own, it's just a mushy base. To make bread, you need structure, right? Look specifically at those red dots forming on the right. Those represent chemical crosslinks. Before these crosslinks form, the polymer chains are just a loose network floating around. They really don't have structural integrity. But the cross-linking process literally ties the chains together into a permanent 3-dimensional web. This is exactly what gives the finished rubber its shape memory and mechanical stability. It is the magic moment the dough becomes the bread. So what actually goes into this recipe? Well, compared to other elastomers, silicone requires remarkably few ingredients, basically just 3 key components. First up, we need those crosslinkers. Sticking with our baking analogy, think of them as the yeast that activates the whole structure, converting the raw rubber into a stable product. Second, we add fillers. This is like adding flour for structure. We use pyrogenic silica, which has a massive surface area, specifically to reinforce the network, or we just use standard quartz to fill up the volume. Finally, we have additives, like stabilizers for extreme heat resistance or custom colorants. And no, unfortunately, chocolate chips are not an approved industrial additive here. But here is an amazing fact. Unlike traditional organic rubber, silicone does not require any organic plasticizers or antioxidants. The base polymer is already tough enough on its own. Okay, part 4. 2 ways to cure. We're looking at peroxide versus platinum catalyzed. We've mixed our dough, and now it is time for the final step in our manufacturing bake, curing. The industry relies almost exclusively on 2 totally distinct chemical mechanisms to trigger those red crosslinks we saw earlier. The crucial point here is choosing the right cure for the right job. On the left, we have peroxide curing. This is the traditional workhorse. It's been proven for over 50 years, gives a wonderfully long shelf life, and is highly resilient during manufacturing. However, the peroxide reaction is inhibited by atmospheric oxygen. That means if the surface of the curing rubber touches air, it might stay incompletely cured and a bit sticky. On the right, we have platinum-catalyzed addition curing. This method is incredibly fast, and it leaves a perfectly dry surface. But its biggest advantage, it doesn't produce any odor or flavor-impairing byproducts. It is completely odorless and tasteless. The catch is that it's very finicky. Even tiny amounts of ambient sulfur or amines in the factory air can literally poison the platinum catalyst and stop the cure entirely. And finally, part 5, everyday materials superpowers. Let's take this from chemistry straight to real-world application. Now that we've traversed all the way from atomic valences to industrial curing processes, let's see how this microchemistry translates into macro-scale solutions. First off, let's talk aesthetics and design flexibility. Because the base silicone polymer is naturally highly transparent, it basically acts as a perfect blank canvas. By adding specific color pastes during that compounding phase we discussed, manufacturers can achieve absolutely any color imaginable. We're talking perfectly clear, vibrant translucent greens, completely opaque industrial blues and oranges, all without sacrificing a single drop of the material's core mechanical strength. But the real superpowers are structural. Remember that incredibly strong 451 kilojoule per mole silicon-oxygen bond we looked at earlier? Because of that, this material boasts extreme high-temperature resistance and incredible low-temperature flexibility. Certain grades are even formulated to be flame retardant, providing vital, life-saving protection in the clothing of rescue personnel. If we use that platinum-catalyzed curing method, the resulting rubber is completely odorless and tasteless, easily meeting the ultra-strict standards required for food baking molds and medical devices. By tweaking the fillers, we get incredible tear resistance, which is absolutely mandatory for things like baby pacifiers and bottle nipples. And finally, its ability to withstand continuous, punishing dynamic stress makes it the only real choice for the violent environment inside automotive turbochargers. It's truly amazing to think about, isn't it? We have taken abundant, simple quartz sand from the Earth, tapped into its quaternary atomic structure, shielded its exceptionally strong bonds, and formulated it into an invisible, hyper-elastic shield that protects, seals, and powers our modern lives. It leaves us with one incredibly exciting question to think about. With the molecular backbone built from sand, what impossible problem will silicone solve next? Thank you so much for joining me on this journey through the science of silicone. Stay curious, keep learning, and I will see you on the next explainer.